487 out of the 10,000 values are out of the 10,000 values, only 487 are less than 0.05. That means that only 400 are significant, but 9,513 are not significant. So you can perform the experiment, because we had seen that the t-test was not significant the first time. The p-value was 0.23. So the t-test was not significant the first time. But now if you perform the experiment a number of times, then you can extract the values that are significant from the 10,000 iterations. So a student can ask, what is the difference between the standard normal distribution and the t-distribution? So show yourself the difference between the two with the 19 degrees of freedom and the 5 degrees of freedom. Then use this code to modify. So far, you can use this code, and then the commands. I have the code here. So the statistic will return the values of the t-test instead of the p-values. The p-values only if you specify to them that you extract using the $sign. So we have the number of repetitions, that is 10,000. Then we want results for 5 degrees of freedom to be in an array, and also the result for 19 degrees of freedom array. So for I in 1 up to, because we are iterating 10,000 times, for I in 1 up to the 10,000th value, we have the values of x when the degrees of freedom is 9. We are generating them from the normal distribution. We're generating random numbers, 20 random numbers with mean 100 and standard deviation 15. Then the 5th degrees of freedom, again, we are generating 9 values with the mean 100 and the same standard deviation. So we want the ith result for when the degrees of freedom is 5, where we get the t-test for these values, the 20 values, and we're testing that mu equals 100. So we are extracting the statistic. We're not extracting here the p-values, but you can as well extract the p-values if you wish. Then here we have for the 19 degrees of freedom, again, we're using the t-test. Then the values at which are 9 of them. When we have 19 degrees of freedom, we are testing that mu equals 100, and then again we extract the test statistic. So then we can plot, still running, then we can plot that density, and then we get the lines here. So we have these two boundary lines that we have just added on top of the density function. So a simple extension, now sampling from normal with the mean 105. Any question up to that point? Any question before I continue? Any question before we proceed? Okay. Now, if you're sampling from normal distribution with mean 105 and standard deviation 15, and we are testing the hypothesis that mu is 100. So the testing against this should produce significant results. So when you increase whether you increase the value of n or will it affect the power function of that test? So you can give that a try and see whether it will affect the power of the test. So when you violate the assumptions of the t-test, you might remember 3 assumptions of the t-test, that each of the 2 populations being compared, for instance, if you're testing 2 sample t-test, mu1 equals mu2 versus the alternative that mu1 is not equals to mu2. Alternative that mu1 is not equals to mu2. So the assumption is that each of these 2 populations being compared should follow the normal distribution, and also that the 2 populations being compared should have the same variance, and n should be equal in the 2 populations. So that means that n1 should be equals to n2. We can run simulations in which we violate the 3 assumptions. We run 2 of the possible combinations and determine if they might inflate the value of alpha. And remember, the value of alpha is probability of rejecting the null hypothesis, given that it is true. So where we have the critical region C. So we are rejecting the null hypothesis given that it is true. So we can simulate 7. We have simulations from the exponential distribution when we have equal variance and equal n. From the normal distribution when the variances are not the same but n is the same. Again, from the normal distribution when we have equal variance and an equal n. From the exponential distribution when we have an equal variance and equal n. Then from the exponential distribution when we have equal variance but unequal n. From the normal, both are unequal, and the exponential, again, both are unequal. Then we can generate data with H1 assumption, the alternative hypothesis, and the sigma to see if the violations affect the power of the test. In the one sample example that we have just seen, we sampled from the normal distribution. We got the values of x from the normal distribution. That's what we generated, and then we tested whether the mean is 100. So in order to violate this assumption, we can now sample from the exponential distribution. And remember, the parameter of the exponential distribution, we use the rate. And the exponential distribution has a single parameter, which is the rate, and it is the inverse of the mean and standard deviation. So the rate is equals, it is just the inverse of the mean and standard deviation. So if you want to sample 20 numbers, remember we had n was, in the same example that we had n was 20 and mu is 100. So we are sampling for the t-test. We were testing whether mean equals 100. So here our parameter of interest is 1 over 100, which is the rate. That is 1 over the mean. So if we have equal mean and standard deviation, that is we are saying that if you want to sample 20 numbers from an exponential distribution with mean 100 and standard deviation 100, then you should use, so what we are using is we are generating random variables from the exponential distribution. We are generating 20 with rate 1 over 100. Therefore, now we'll have the t-test will now change. So we have the first variable, random variable x1, 20, and again also another variable x2, which is generated from the same exponential distribution. Then we can perform now the t-test on x1 and x2. Then we are performing we are not performing the paired t-test, we are performing the two sample t-test. Note that simulation 4 poses a difficulty. The exponential distribution has equal standard deviation and mean. So how can you have a difference in the variance but equal means for the two sampling? So first, let us run this, and so this is let's give it name test. Then we can extract p-values and the standard deviation or the test statistic. So we can extract the test statistic and also extract p-value. The test statistic is 1.3086. The p-value is 0.2, which is not significant. And we can also extract the statistic. That's okay. So here we are rejecting the null hypothesis. Remember, here we are extracting from, we are generating the random variables x1 and x2 from the exponential distribution. So they are random again. So you can as well perform this experiment as many number of times as you wish, so that you can get, you can extract the p-values that are significant or the values that are significant. We also have the t-test or the chi-square level. Which one is are we to use? So it depends on the data set that you have. Now let's suppose that you are looking at gender difference in admissions to a nursing program. You obtain a sample of 20 male and 20 female applicants and coded rejection, whether they were rejected as a 0 and whether they were accepted in the program as a 1. You run a t-test on this binary data. So we have male, the values are as follows, the 20, females the same. Then when you run the t-test, you get t at 38 degrees of freedom, because we have 20, n1 is 20 and n2 is 20, so n is 40. So we have the degrees of freedom here is n minus 2, or n1 plus n2 minus 2, the total. So we have 38 degrees of freedom, and then you get the t-value as 2.307 and the p-value at 0.027. And therefore, of course, here you decide that you are rejecting the null hypothesis, that we are rejecting that the mean for male and female are the same. So we accept the alternative, or we fail to reject the null and accept the alternative that the means are not the same. Female. So the data, our data set is not, the data is not numeric but categorical. So you should have used the chi-square and not the t-test. So you know that the reviewer is correct in the sense that chi-square is probably the standard choice for this type of data. But you wonder, would it make any difference at all, whether when you perform the chi-square test, whether you'll get that you are rejecting your null hypothesis. So is your alpha inflated if you use the t-test? And what is the relationship between the t values and the chi-square values in this situation? So to do that, you can use a scatter plot. And then is your power affected by your choice of the test, whether the power of the test has been affected by the fact that you have a t-test or the fact that you're using the chi-square test. And what is the effect of the Yates correction? So these are the commands that you might use to complete this assignment. So we have here, we are generating 20 binary data points. So because they are binary, it's either that the person was accepted to the program or not. So we have 0 or 1. Therefore, this is a binomial that and each have the same probability of occurrence. So we have that male, we are going to get male from the binomial distribution. So we have for male, we have R binom, and we are generating 20, 1, and then P is 0.5, females the same. The binomial distribution, 21 and 0.5. So first we generate the two data set, data for male and data for female. So this, the next line will generate the frequency table. We have the frequency table that values of 0 are 12 for the first row, that is for male, and values of 1 are 8. So they are all the same. Just have this here so that when you're running, then you see the actual results. The next two lines here, we are performing now the chi-square tests, but first with the Yates correction and the second one without the correction. So we call this results.cp chi-square test with the correction, because by default a chi-square test has the correction, so you do not have to specify the correct equals true, because by default it is true. Then the second one, we have to specify correct equals false, so that is without the correction. So let's see these results. The p-value is 1, chi-square value is 0. Then for the second one, the same. Now we perform the t-test, then get the result for t-test. So again, here we have p-value 1, so there's no difference here with the chi-square end and the p-value. So beyond these p-values, let's consider the following situation. You're running an experiment, and after running 20 participants, you perform a statistical test. So if your test yields a significant result, then you stop. So if you have a significant result, then you stop, and then you say now that your results are significant, therefore you accept, you reject the null hypothesis, etc. Then you make some conclusion. So you stop and then you publish your work. What happens if the results are not significant? Do you just give up, or do you say, well, maybe I did not have enough power, or should I run more subjects? You maybe increase the number of the sample size, or if you decided to do so, so what will be the consequences? So here is a sample code that checks the significance and number of times. So you can check the significance and number of times. So you don't just stop there, but you check the significance and number of times. Then you can add the number of subjects, that is n. You can increase the sample size if the results are not significant. So the number of times to check for significance. So we check number of times equals 1. The number of subjects to be run, we have n extra is 20. That is the extra time, the extra subjects. Then n times equals 0. Then I win, flag, etc. So we are first initializing these values, and then we're repeating this 10,000 times. Our result, we are going to use the same above. .t, that's an array of dimension 10,000, and then for I in 1 up to 10,000, we have flag 0 times is 0, and then xc we are generating from the normal distribution 20 random variables, random numbers with mean 100 and standard deviation 15. Then while flag is 0 and times is less or equals to check times, then we have that times we add 1. Then the ith result from the t-test will now be the t-test for the values of xc, that's the values that we have generated from the normal distribution, would mean 100. And here we are extracting the p values. And if this result, if each of the result, if the p-value is greater than 0.05 and flag is 0, then we'll have that xc, we take the values of xc, then random number, and then from the n extras, again, remember n extras we had identified here as 20, with mean 100 again, and standard deviation 15. And if the result is less than 0.05 and flag is 0, then pick flag 1, and I win will be I win plus 1. Then we need now to get a table of which of these p-values are less than, how many of the p-values are less than 0.05. So we have, for the true, we have 791 out of the 10,000 generated values. Out of the 10,000, we have 791 that are significant, while 9,209 are not significant. We have some homework. There are a number of variables to consider. That is the check time. That is the number of times that you will pick into the results. N extra, the number of extra subjects that you're going to add. Theta is the distribution that you're sampling from. So your task here is to run enough simulations varying the provided code. So the code that we have, you can just vary it so that you can tell what are the effects of the 3 variables that you have just described. The effects of the check time, n extra, and theta, the standard deviation. Use one paragraph to describe this problem and why should we care, why we need to change the values of the check times, n extra, and standard deviation. So you can try that one. We also have another example here under the Bayesian inference. So can a p-value that is between 0.03 and 0.05 be more consistent with the null than with the alternative hypothesis? So what happens if you specify an alternative hypothesis, e.g., the effect of manipulation in delta is 10 and the sample size is 200? So we have that alternative result.1, that is the first result. We want it in form of an array with the dimension of the number of times that you're repeating, you're iterating. Then the number of subjects is 200. Effect size, we have that delta is 10. Then for I in 1 up to the number of iterations, so we have x dot 1, that is n random numbers from the mean, which is 100 plus delta, and standard deviation 15. So here we're only changing our mean. The original mean, we had mean of 100 and standard deviation 15. So we're only changing the mean by adding some delta, value of delta. Then now we are generating from the normal distribution n, we're generating 200 observations with mean. This will be 110 because we have already specified our delta value to be 10 and standard deviation 15. Then we can perform the t-test. And then the t-test for this random number, for the 200 random numbers, and pick for testing whether the mean is 100 and pick only extract the p values. So we get a table here of the results that are greater than this and the results that are less than 5. So based on this simulation, you will have to run a number of combinations of delta. So you can change the values of delta and also the values of n. Given that an experiment, your friend maybe finds a p of 0.5, then should the researcher reject the null hypothesis? Then we have the central limit theorem. Is there any question on the Monte-Carlo simulation? Okay. So the central limit theorem states that for a random sample of values x1 up to xn from a population of the random variable x with mean mu and variance sigma squared, we say that Tn will tend to a standard normal distribution as n increases, that is as n tends to infinity. Then we'll have that the distribution will be Tn square root of x bar minus mu over sigma. Then we have one example on the same. For x, which is a discrete random variable, which takes values 1, 2, 3, 5, and 7, with probabilities, those are the probabilities generated. Each probability 0.05 for value 1, 0.1 for value 2, etc. Generate 250 samples of size 5, 9, 13, and 7. Then write an R program which will simulate the distributions of the statistic of the above sample. So you can try and run this code at home. So we have that first here we are setting seed because we want to use the same random numbers generated. Then the first sample is in form of a matrix 0, and then we have 250 by 30. Then this is the data 250 column and row equals starting. Then for I in 1 up to 250 values, so we have sample I, that is the ith in the ith column. So this is picking all the values in the ith column. So this sample, and we have 30 with this specific probability. The population mean, the population standard deviation, we also can specify that population mean is the mean of using the apply function sample 1, 2, and mean, and then the standard deviation the same. So when you want to simulate 250 samples of these sizes, we use a function. It will be a function of n, population mean and population standard deviation. Then we first set seed, then our sample, we get the matrix, then for I equals 1 to n, then we have the same sample where we specify also the probabilities, then mean and variance, just like we have seen. And now that when we are using the central limit theorem, Tn is the statistics that we're interested in its distribution. So the formula here is we have square root of n So we have square root of n standard deviation from this formula, that is x bar minus mu divided by the standard deviation. So here is we have, you can just put this the same here. So we multiply, this is the same as over sigma x bar minus mu. So it is the standard deviation of n, because we already specified the value of n up there. Then the population standard deviation that we already specified, square root of n divided by population standard deviation, then this is multiplied by mean and the population mean that we are testing. So we can print the mean of t and the variance. Then we can plot histogram of Tn and the limits for x. We have the minimum of Tm minus 2, then the maximum plus 2. Then the y limits, we're just giving the limits. We're specifying the limits of the y-axis and the x-axis. Then we're plotting t. Then plot is true. Probability is also true. Then we give it a title. Then we can add the density line on top of the histogram. You can also get the normal QQ plot and the QQ line for t. So this will give you can give the title for this as normal QQ plot, and then the parameters. So we can get these values n, that is n, and population mean and population standard deviation. So you can try and run this code at home and see the results of the same. That's all for today, unless there is a question. Any question?